We have seen how to implement a publish, subscribe, or observer scheme through a particularly elegant technique, the observer pattern. We've also seen, however, that this technique, this architectural technique, has some limitations. And now we're going to move to the next step up. We're going to see that by gaining a level of abstraction, we can actually have an even more elegant and simpler solution. We've seen in particular that the limitations of the observer pattern, at least in its basic form, which can be somewhat improved, are that publishers must internally know about subscribers, not such a big deal, but a little bit worrying. More significantly, that a subscriber may subscribe, again, in the basic form of the pattern to at most one publisher, to at most one operation, and more fundamentally, that the solution is not a reusable solution. That is to say, it's not something that you can put into a library and reuse as it is for every publish-subscribe application, but it's something that you need to code anew, code again and again for every publish-subscribe application that you may have. And now we're going to look for a next level of mechanisms that essentially addresses all these issues and on top of that brings us more advantages. So the way it's going to work is the following. So I'm going to describe how to use it. I'm not going to give you all the details of how to implement the solution, although those are partly in the textbook and you can look up the code and see exactly everything. I'm going to show you first, however, how to use this mechanism. So it's going to be extremely simple, and it's going to be based on a library that you can access as part of the Eiffel libraries, which provides a standardized event-driven programming mechanism, a standardized publish-subscribe mechanism, addressing all the issues that were mentioned on the previous slide. In particular, the solution is going to be completely reusable. That's what it means to have a library. You just use the library. Now, in fact, this library is extremely simple. It has just one class. The class is called event type, and we're going to see how to use it. It's going to be used on both the publisher side and the subscriber side. So each event type is going to be an object. So be careful here. It's not that each event is going to be an event. It's going to be an object. When I click the mouse, I don't want this to be an object. Why? Well, think about it for a second. The answer is that in terms of performance, it would be far too much. In a typical session, for example, in an interactive application, we're going to have lots and lots of events. In fact, every time we move our mouse, it's a new event, which indicates the new position of the mouse. So pretty quickly, in a long interactive session, we would have tens of thousands, maybe hundreds of thousands or more of events. And this is just inefficient because, for example, when we move the mouse, what really counts is the initial position of the mouse and the final position. And we don't, most of the time, we don't need to record all the intermediate events. So it would be quite bad to have to create an object for each one of these events, and then the garbage collector, of course, would have to get rid of them. So it would do so. There's no particular problem for the programmer, but in terms of performance, it would be pretty bad. So what is actually going to be an object is not an individual event, but an event type. That is to say, not one particular mouse click, for example, but the notion of a mouse click, or maybe more precisely, a click of the left button of the mouse. So that's an object. Then we also need the notion of context, and we will need context objects. What's a context? Well, if we go back to the standard example of a GUI application, of an interactive application, well, not all mouse clicks are created equal. If I click here, it's not the same as if I click there. In other words, an event depends, or the handling of an event depends on the context in which the event occurs. And typically in an interactive application, the context is going to be a graphical element, like for example, this little window here. And so that's a context. The notion can actually be generalized. It applies also outside of the example of a graphical interactive application, but you see it quite clearly in that particular example. A context is a graphical object in which an event, or specifically an event type, has a certain meaning. It must be processed in a certain fashion. And then, when we have an event of a certain event type occurring in a certain context, for example, a left click occurring in the map, well, the general idea of the publish-subscribe scheme is that we will want in advance to define what action is going to be executed as a result of the event of that event type occurring in a certain context. And so this is our third concept here, the concept of an action. For example, in our running example, we might want that every time the user clicks on the map, so click is an event of the event type left click, the map is the context. Every time such an event occurs in the context, we might want to specify that the routine find station from our model, from our domain model or business model in the MVC sense, be executed. Each time the user left clicks event type on the map context, we want to execute the routine find station, which is an action. So this is how we're going to work. We are going to work with triples, each one of which is made of an event type, a context, and an action. And the association of such elements, one event type, one context, one action, essentially gives us the publish-subscribe scheme. So ahead of time, at the beginning of execution, we are going to subscribe certain actions for certain event types in certain contexts. And then what does it mean to execute the application in such a scheme? It's simply to wait for events to occur, and anytime an event occurs, we're going to find out where it occurred, that's the context, what is the type of that event, and as a result, we are going to execute the associated action. So that's a very simple and elegant way to implement a publish-subscribe scheme of programming. It's a complement to the kind of control structures that we had in previous lectures. We're not saying first do this, then do that, or repeat this until that, or if this, do that, else do something else. We are saying whenever an event of a certain type occurs in a certain context, execute a certain operation. Now, to implement this, we need something else than what we've defined so far in the programming language. Because we'll need ways to represent all these three kinds of elements, event types, contexts, and actions, as entries in a table. And in a table, we need references to objects. So for the first two cases, we don't have a problem. We will represent event types by objects. That's going to be pretty straightforward. The context, well, if we're using a graphical library such as Eiffel Vision, which is the Eiffel graphical library, or the equivalent in Java, say Swing or something like that, we also have objects. But for actions, well, we have routines, right? Find station is going to be some routine in the Eiffel code, which determines how to find the closest station to a certain x, y coordinate point. In this case, it's probably Polyterrasse. Well, we have a routine that does this, but the routine is not an object, it's code. And so we need a way to represent code as objects, so to speak. We need a way to encapsulate routines, that is to say code, in objects, and that is exactly what agents are going to give us. So if you look at the Eiffel Vision library that I just mentioned, it does this in the way shown here by on left click and so on, but we're going to, with the Eiffel event library, to use a more simple and more general scheme where we have just one generic class and two features. So it could hardly become simpler. Actually, it could not be simpler than that. Subscribe is the mechanism that the subscribers are going to use to say, whenever this event type occurs in that context, I want to execute that action. So we subscribe an action to an event type in a context. And publish is of course what happens on the publisher side. And the publisher side, the publisher can at any time say, now trigger an event of this event type. So here's the way it works. At some point in the program, with declarations accessible from other places, of course, we are going to declare a certain event type. And we can do this, of course, for as many event types as we like. This is how we declare the event types. How do we declare an event type? Well, we use the class event type, and that class is generic, as you can see. It takes a generic parameter that is constrained by tuple, meaning the actual generic parameter must be a tuple, and more precisely, in this case, it's going to be a tuple of two integers. Now, what's a tuple? In this case, a tuple of integer and integer is a pair of two integers. We're going to see the details of tuple types in the next segment, but here we can see the basic idea. When we write tuple of A and B, where A and B are types, we mean a new type whose elements are pairs, and each pair has a first element of type A and a second element of type B. Actually, a tuple can have more elements than that. If we say tuple of AB, we mean any sequence of any length at least equal to 2, such that the first element is of type A and the second element is of type B. So we declare, coming back to click, we declare click meaning the event type click my mouse, or maybe left click my mouse, in which case we would call it left click, an event type corresponding to events which represent clicking the mouse. And why the tuple of integer and integer? Well, it's very simple. When we click the mouse, when the user clicks his or her mouse, we will want to know the information that they clicked the mouse at right now, so that's an event, but we will want more information than that. It's the notion of event argument, which I mentioned in the last segment. We will need to know that there was a certain abscissa, a certain horizontal ordinate x, and a certain ordinate, vertical coordinate y, and so we need two integers if everything is measured in pixels. So that's why we have integer and integer as the components of the tuple. So in general, event type takes a generic parameter which is a tuple, and that tuple represents the types of all the arguments that we need to characterize the event fully, an event of that type fully. So that's what we need to do first, declare the event type. Then we are going to create an object which is an instance of that type. Create click, because we need one, and we need only one. And then on the publisher side, we're going to do one thing, and on the subscriber side, we're going to do something else. So let me start with the subscriber side. There's some subscribers somewhere which says, I want to know about any event of the type click that occurs in a certain context, and so whenever that occurs, I want to execute find station. Well, to do this, the subscriber just says, it's about as simple as it can get, click.subscribe of agent find station. We are ignoring the context right now. We'll see how to integrate the context in a second, but here we just say click.subscribe of agent find station. So what does it mean? Well, click is the event type. So when I say click.subscribe, I'm saying I'm interested in your events, you there. I want to subscribe to them, and what do I subscribe? Well, I subscribe one of my routines. So agent find station, and this is our first direct encounter with the mechanism introduced in this lecture, agents. Agent find station means an object that essentially represents the routine find station. That's what it is. So click.subscribe of agent find station means, hey you, event type click. I'm interested in you, and whenever an event of your type occurs, I want to execute my routine find station. That's all. It's very simple. Subscribe a certain operation represented by a routine to a certain event type. And then during later on in the execution, of course, the publishers are going to decide to trigger certain events. So for example, you have the graphical part of the software that detects when the user has clicked his or her mouse, and whenever that occurs, is going to publish the event. And how do we do this? Well, we use, of course, the same event type, click, and we use the routine publish. And what does publish do? It publishes the event with arguments. So here we see the event arguments, x coordinate and y coordinate. This is the previous idea of having the x and the y of the mouse position. And this thing in brackets here is a tuple. X coordinate, y coordinate. That's a tuple corresponding, of course, to the type tuple of integer and integer. So that's it. This is really all there is to do. On the subscriber side, we say subscribe me, subscribe my routine find station, for example, to a certain event type. And on the publisher side, whenever the publisher wants to publish an event, to trigger an event, for the same event type, it says publish me, publish, or rather publish yourself, with the arguments that I'm giving you now. Very simple. And this is all provided by the library class event type. You are absolutely welcome to look up the class and the implementation of the routines publish and subscribe. I'm not giving you the implementations here of publish and subscribe, but they're very simple, and they're about keeping an association in a table between event types and agents. So you have tables that for each event type, and we'll see how to associate the context in just a moment, but basically for every event type, we associate an agent, and what subscribe does is this association. For the event type, in the table it puts the agent, and what publish does is that in the table it uses the information to publish the event, an event of that corresponding type, with the right argument. So, for example, we could do something like this, and you might think that I was hiding something from you because the context suddenly disappeared, but in fact it's very simple. We don't need to build in the notion of context in the library itself. It's just in the way we use the library that is going to be there. So, for example, if I want to make sure that find station is only used to react to the left click event type in the context Zurich map, we are going to make the event type local to a context represented by a graphical object like Zurich map. So Zurich map dot left click dot subscribe of agent find station. So that's what the subscriber does, and the publisher does whatever, the same thing as we saw before. So that's really all there is to do to use the event library. In the end, as you can see, it is much, much simpler to use than the observer pattern. There are no new classes to write, and it's completely reusable because it's entirely based on two features, subscribe and publish, from a library class event type, which is written once and for all. Of course, there are a few more features like unsubscribe, but these are the basic two. So with the observer pattern, we needed to write a descendant of subscriber in my class. So we had an explosion of classes. Also, it was quite hard to handle arguments. As we saw here, we reused the existing routines directly as agents. That is, what's really important here, you can think here of the MVC pattern, is that find station is directly a routine from the model, the M of the MVC. We don't have any glue code to write. In the use of the observer pattern, we had to write a subscriber class, and then that subscriber class would have a routine which calls find station. Here we don't need any of that junk. We can directly use find station. So we can have lots of variants. We can directly subscribe to an event type. We can subscribe to the Paris map. Previous slide it was Zurich map. We travel a little bit for variety between Paris and Zurich and back. We can also have a few more variants that we're going to see in the next segment. So I leave this question marks mysterious here. Well, maybe you can guess what they're about, or maybe not. It's not absolutely trivial. This is simply the case in which we have a procedure called your procedure, which instead of 2 arguments, like find station, has 4 arguments. But the two arguments that we want to associate with the x and the y of the event location, of the click location, are the second and the third. So it's just as simple as that. And we'll see this mechanism of question marks in detail in the next segment. So you can also subscribe someone else's routine. It doesn't have to be a routine of the current object. It can be something that occurs somewhere else. Here's another example of application of agents. It's in a completely different domain, mathematical software. So this one has absolutely nothing to do with the kind of examples we have seen so far. It's not observer, it's not publish subscribe, it's not even an interactive application or a graphical application. It's just purely numerical software, and is going to help us appreciate more the power and versatility of this very general agent mechanism. The problem is to integrate a certain function. So we have a certain function f, which you can see its curve here, or part of it in the figure, and we want to integrate it over a certain interval from a to b. And so we are going to apply the usual technique for integrating a function. Of course, there are a number of mathematical variants, but the basic idea is okay. Numerically, it's the one that is illustrated by this figure here. That is to say, we are going to do an integration the way Leibniz and Newton were doing in their days, by taking little rectangles and approximating the entire surface represented by the integral here by the sum of the surfaces of these little rectangles. The rectangles are going to have widths called step, and of course the smaller step is, the more precise the integral is going to be. So at each point in time, we take value x, which is between a and b, and we essentially compute f of x times step, and this gives us the area of this little triangle here, and by doing this repeatedly we get the entire yellow area on the figure. So that's what we do, and agents are going to be essential here because they enable us to represent f. F is a function, so I said it's a function in the mathematical sense, but it's also a function in the programming sense, in the Eiffel sense, and so it's going to be declared with a new type, function here. I'll explain the parameters later on, but function and procedure are agent types. So an agent represents either a function or a procedure. In general, it represents a feature, particularly a routine. So we are going to declare f as a function, and what does it mean? Well, it's a function that takes as argument a real. The arguments are always going to be represented by a tuple, so tuple of real represents a single real, and then it returns a real as well. Like, for example, the square root routine or the cosine routine. We can ignore the first parameter for a second. And then integral takes f as an argument plus a and b, which are the bounds of the integration. And so what do we do? From x initialized to a until x is greater than b, we're going to compute f dot item of x times step. Then we'll do I receives I plus 1, and we'll compute x as a plus I times step in order to get to the next x. So the key part, of course, is this term here, which represents this value multiplied by this step. So it represents f of x, f dot item of x. This is mathematically f of x, and then we multiply it by step. So in mathematics, we would write something like sigma for I from 0 to some n of f of a plus I times step times step. Okay, this is what we're computing, and here we have a very direct translation by having f dot item of x. This is the value of f of x. This term, of course, is x. And so that's all. That's all that we need to do, and you can see how practical it is to have the ability to declare variables like f, which represents not objects in the usual sense of data, but objects that themselves represent operations. A little detail here, a little numerics question. This really has nothing to do with the rest of the discussion, but it's really important. It's a really important point in practice in numerical programming. Why don't we just increase x by step? This is what I said informally. When we go from I to I plus 1, from this point here to the next, we're just adding steps. So why do we recompute from scratch, so to speak? X receives a plus I times step, instead of just adding step to x. Think about it. The answer is a numerical answer. It has, in fact, nothing to do with the rest of the discussion, as I mentioned, but it's important in practice. If we do x receives x plus step, as shown on the right, we're going to have a small numerical error. As you know, the representation of numbers is not exact on computers, the representation of rational and real numbers. So it's okay, it's going to be a very small error, but we accumulate it if we do this 10,000 times, 1,000,000 times or more. And so as a result, it could be very bad. We could have a serious drift in the result. With the technique that we are actually using here, we still have, of course, a little error, but we recompute x from scratch each time, and so we keep the error minimal. These kinds of errors are very important. There are many famous software-related catastrophes for that kind of reason. So be careful, and in practice always remember that when you are using so-called floating point operations, that is to say operations that are not exact on the machine, make sure not to accumulate errors, because one numerical error or a small number of numerical errors are okay, but an accumulated number of numerical errors can cause catastrophes. Here's our last application of agents for this segment, iterating. There are other ways to iterate. You saw in particular the across mechanism in Eiffel, but here we have a more general, a completely abstract way of iterating. Basically, we want to know whether a certain property holds of every element of a data structure, such as a list. But we want a single mechanism to do this. And the single mechanism exists in the Eiffel-based library. It's for all. So for all, as the name suggests, is a function that's going to tell us whether a property holds for all elements of a certain list. And in one example, we want to know whether all elements of a list of integers, int list, are positive, whether this routine is positive, which takes an argument n and tells us whether n is positive. In another example, we are going to work with a list of employees, emplist, and we want to know whether every employee in the list is married, where is married is a feature, a Boolean valued query of class employee. So if you think about it from a language standpoint, it's not absolutely trivial, because we want to be able to apply the same mechanism, the same for all mechanism, in one case to a routine that takes an argument, and the question, the property that we're assessing is a property of the argument. In the other case, we want to apply the property directly to an object, to use as target. Well, here is how it works. We can use for all for integer list with agent is positive, with question mark. I'll explain the question mark in the next segment. And for employee, we can also use for all with an agent, which is the agent built from the query is married in the type employee. We will see the syntactical variants in the next segment, but it's really interesting to see that we can use a single mechanism for all, a single routine, which is in class linear, I believe, in the Eiffel-based library. You can check it now, to do both kinds of iterations. Indeed, in class traversable, which is the ancestor of all list, sequence, and other such classes, you will find a number of such iterators, for all and there exist, which apply to Boolean queries, and do all and do if, which apply a certain action to all elements of a list. So what we've seen in this segment is the notion of agent, a powerful high-level mechanism for treating computations as objects. We look at routines, which are computations, which describe computations, and we treat them as objects so that we can play all kinds of games with them. We can put them, for example, in data structures, such as arrays or lists or tables. And there are lots of applications. We saw 3 of these applications, and it's really remarkable how different they are and how versatile the agent mechanism is that enables us to use the same techniques in all these different areas. Event-driven programming was the first, with a really appealing alternative to the observer pattern, better in just about every respect. Actually, I cannot think of any argument for observer pattern over the event library, and personally I'm quite determined never to write an observer pattern ever again in my life, even though it's an elegant and powerful technique. But there's an even more elegant and more powerful one. Then we have seen applications to numerical analysis, quite typical of how we manipulate functions, mathematical functions using agents, and iteration. In the next segment, we are going to see a little bit more of the internal mechanisms that make all these exciting applications possible.